Great, thank you all so much for being here. Before I get started, I want to thank my committee members, Dr. Sharnova, Dr. Howard, Dr. Fye, and Dr. Smart for their guidance throughout this entire process. And then I especially want to thank my advisor, Dr. Matthew Gambale, for his support and for everything that he's taught me over these last 5 years. And so I'm going to be presenting on my thesis work today, data-driven personalization techniques to account for heterogeneity in human-machine interaction. And so why is personalization necessary in human-machine interaction? Well, as we all know, humans are a very diverse species, and this diversity is due to different genetics, which can produce different biology, different personalities, and different abilities. Additionally, humans have a high potential for neuroplasticity, which can also mean that we can change and adapt to our environment, and this increases diversity. And so this diversity from an evolutionary and biological perspective is great because it leads to species survival and even flourishing. However, this diversity can pose a problem for machines that will have to work closely with end users. These machines will have to understand the diverse characteristics of the end users that they are working with so as to optimize the human-machine relationship. And so one-size-fits-all models that are trained on a bunch of human data and then the same model used to produce the behavior for the robot when working with every single end user likely won't be effective in situations in which the heterogeneity of end users plays a large role. And so my solution to this problem is to enable robots to gain a personalized understanding of the end users that they are working with. And so we can do this by either passively collecting data from the end user or actively querying the end user for information. My goal is for then the machine to personalize its actions and behavior based upon its understanding of its end user. And machines shouldn't just consider end users as isolated entities because every end user is part of a larger population, and where the end user falls within this population can also inform the machine's model. Additionally, there are many domains in which the safety of the end user must also be reasoned about. So for example, in healthcare domains, machines must not only understand the biology of their specific patient, but must also take into consideration the safety of the patient. And so in my work, I aim for machines to be able to adapt to heterogeneous abilities, preferences, and biology of end users. And of course, abilities, preferences, and biology are not an exhaustive list of all the ways in which end users can be heterogeneous, but they represent many of the different characteristics that machines will have to account for in human-machine interaction scenarios. And so to summarize, the objectives in my work are to enable machines to learn a personalized model of their end user and utilize population context to inform this model. And then once the machine has this model, my goal is for the machine to personalize its actions and behaviors to fit the needs of its specific end user. And then lastly, in my thesis, I aim to validate all of my approaches in large human subject studies with real human subjects to make sure that they actually work with human end users and human data. And so in my thesis, I investigate various contexts and situations in which machines will have to adapt to heterogeneous abilities, preferences, and biology of end users. Prior work has shown that humans tend to be heterogeneous and suboptimal in learning from demonstration paradigms. And specifically, prior work has shown that humans are heterogeneous and suboptimal when providing demonstrations in a robot-centric LFD paradigm in which they're tasked with providing corrective feedback to the robot. And there's been no prior approaches that have investigated how to account for this heterogeneous suboptimality in robot-centric LFD. When a machine is tasked with teaching a novice human some new task, the machine will have to understand the abilities of its student learner and adapt its instructions accordingly. Previous approaches have introduced frameworks for robots to teach a novice learner. However, many of these frameworks only work for simple tasks and utilize simple instructional strategies, for example, selecting the best lesson plan. And there's been a lack of prior work in providing personalized and adaptive feedback to suboptimal humans in an LFD paradigm. Prior work has shown that end users tend to have heterogeneous preferences with regards to the behavior of autonomous vehicles. And it's been shown that driving style of an autonomous vehicle is particularly important for acceptance and trust, and that an end user's own driving style influences their preference for the autonomous vehicle. And more recent work has shown that not all end users necessarily want an autonomous vehicle to exactly mimic their own driving style. And so there's been no prior work that has created an architecture to optimize driving style with respect to an end user's own driving style and other relevant latent characteristics. Healthcare is an example of a domain in which machines will have to adapt to the heterogeneous biology of their patients so as to optimize patient care. Prior work has investigated approaches for personalizing the care of patients and has shown that active learning can be effective for efficient personalization. However, there's been a lack of prior work that considers both personalization and safety of the patient during active learning. In my thesis, I aim to fill these gaps in prior work. And I say that personalized algorithms that account for heterogeneity amongst individuals will improve upon the human-machine relationship across many domains, including healthcare, autonomous vehicles, and learning from demonstration paradigms. To support this thesis, I introduce 4 research aims. In my first aim, I investigate how we can account for heterogeneous and suboptimal abilities of end users in learning from demonstration paradigms. And I introduce an approach for learning from suboptimal demonstrators via personalized embeddings. In my second aim, I investigate how machines can provide personalized instructions to suboptimal end users to improve upon their suboptimality. And I introduce an approach for personalized robotic teaching of suboptimal novice humans. In my third aim, I then extend these approaches to account for heterogeneous preferences amongst end users in an autonomous vehicle domain. And I introduce an approach for personalization of autonomous vehicle driving styles via both mimicry and modulation. And then lastly, in my fourth aim, I investigate how we can impose safety constraints in safety critical domains in which the machine also needs to personalize to its end user. And I introduce an approach for safe meta-active learning for healthcare. And so I'll first talk about my aim 1, improving learning from demonstration via personalized embeddings. And so in learning from demonstration, a human demonstrator provides a set of demonstrations to the robot, and then the robot can learn some novel tasks from these set of demonstrations. And so learning from demonstration is great because it can increase the accessibility of robots for non-roboticists. Non-roboticists don't need to understand exactly how the robot works or need to know how to program, but can still teach the robot new tasks via LFD. Prior work has shown that humans tend to be heterogeneous in various ways in an LFD paradigm. First of all, humans tend to have heterogeneous preferences for how they want a robot to accomplish a task, which can result in heterogeneous demonstrations. Additionally, humans tend to be suboptimal when providing demonstrations to a robot learner, which can make it more difficult for the robot to learn. And so I'll talk later on in my thesis about how we can account for heterogeneous preferences. But first, I'm going to discuss how we can account for end user suboptimality in LFD. And so human suboptimality in LFD stems from several sources. The correspondence problem states that humans and robots differ in their physical embodiment, and therefore it can be difficult for a human to determine how best to provide high-quality demonstrations to a robot learner. Additionally, humans rely on heuristics when faced with uncertainty, and they also have preconceived notions about what good demonstrations look like, both of which can result in suboptimality. We break learning from demonstration into 2 main types. The first is human-centric LFD. In human-centric LFD, the human is in control and drives the interaction and provides direct demonstrations to the robot learner. The most common example of this is behavioral cloning. And so the upside to behavioral cloning is that it tends to be fairly intuitive to the end user because they're in direct control of the robot and providing these direct demonstrations. However, the downside is that prior work has shown that human-centric LFD results in quadratic errors due to problems with covariate shift because the robot is never taught how to recover when it moves outside the distribution of states induced by the demonstrations. Robot-centric LFD overcomes this problem. And in robot-centric LFD, the robot rolls out its current policy and the human provides corrective demonstrations at each time step. The most common example of this is dataset aggregation, or DAGGER. And so the upside to DAGGER is that we have only linear errors and no regret guarantees. However, because the robot's not actually responding when the human is providing this corrective feedback, it can be less intuitive to the human, and this results in suboptimal demonstration. And so in my work, I investigate how we can take a personalized approach for accounting for suboptimal demonstrations. To do this, we imagine that sometime in the future, a human will go to the robot store and they'll buy a new robot and they'll bring it home and they'll want to teach this robot how to accomplish novel tasks within their own home. However, because the human has never actually worked with this robot before, they likely won't understand how to provide high quality corrective demonstrations to the robot. And so to solve this problem, we first will instruct the human to teach the robot to provide demonstrations on a set of simple known tasks with known optimal demonstrations. Based upon the demonstrations that the human provides in these tasks, we then learn a personalized embedding that describes the way in which this specific demonstrator is suboptimal. Then in future novel tasks, we can use this personalized embedding to map their suboptimal demonstrations to better demonstrations. We call this approach mutual information-driven meta-learning from demonstration, or mind-meld. And we demonstrate our mind-meld approach in a driving simulator domain. In this domain, the agent rolls out its current policy on these predefined tasks, and the human provides corrective demonstrations at each time step, which may be suboptimal. Based upon these demonstrations that the human provides, we then learn this personalized embedding describing the suboptimality of the demonstrator. Then on future novel tasks, we can use this personalized embedding to map their suboptimal demonstrations to better demonstrations. And so we call these predefined tasks with the known optimal demonstrations calibration tasks. And these tasks are meant to be representative of the task space. And so we train our mind-meld architecture on the demonstrations provided in these tasks and the known optimal labels to simultaneously learn the personalized embeddings for the demonstrators and the mapping from the suboptimal demonstrations to better demonstrations. And so here we see our mind-meld architecture, which learns its personalized embedding and outputs the difference between a demonstrator label at time t and the optimal label, with a downstream effect being that the agent can better learn from these improved labels. The way this works is we feed in a sequence of labels into our bidirectional LSTM, which outputs an encoding Z. This encoding Z, along with the embedding W, are then fed into subnetwork F sub theta, which outputs this difference. We additionally include subnetwork G sub phi, which is necessary to maximize mutual information between the learn personalized embedding and the way in which the demonstrator is suboptimal. And so now that we've developed this framework, we first want to verify that it actually meets the objectives in my thesis of enabling a robot to gain a personalized understanding of its end user, utilizing population context, and ultimately improving upon the human-machine interaction. And so the way we do this is we conduct a synthetic study. And so we create calibration tasks and determine the optimal demonstrations for these tasks. We then create a set of synthetic demonstrators and assign suboptimal tendencies to these demonstrators. Based upon their assigned suboptimal tendency, we then can produce synthetic demonstrations. We next train our mind-meld architecture on this data, and we learn our embedding space. And so we find that each point in the embedding space is able to uniquely represent a demonstrator and the way in which they're suboptimal. We additionally find that demonstrators that are similar in the way that they're suboptimal, they tend to cluster together in embedding space, suggesting that our model is able to utilize population context to inform its mapping. And then lastly, we find that we are able to improve upon suboptimal labels by 54%, suggesting that the agent will be able to better learn from these suboptimal demonstrators. And so my last objective in my thesis is to ensure that we validate these approaches in large human subject studies with real human subjects. And so that is what we do next. We conduct a human subject study in our driving simulator domain. And we first conduct what we call a calibration study. And in the study, we recruit 76 participants to complete our calibration tasks. And then from this data, we learn the MyMeld network parameters. We then freeze these parameters and we conduct a test study to compare an agent trained via our MyMeld approach to baselines in human-centric and robot-centric LFT. And so here we see the results from our study, and we show here in blue that our MyMeld approach results in a significantly lower average distance from the goal compared to the baseline algorithms. And we additionally show that our MyMeld approach is able to achieve a higher probability of reaching the goal once, twice, 3 times, and 4 times throughout the course of the study. And then lastly, we find that our approach is rated better in terms of subjective metrics, including workload, likability, perceived intelligence, and trust. And so we've shown in this work, in keeping with the prior literature, that humans do in fact struggle to provide high quality corrective demonstrations to a robot learner, and that our MyMeld approach can effectively correct for these suboptimalities. However, we believe that in certain circumstances, correcting for suboptimality under the hood may not be the best approach. Because we're producing high quality results from suboptimal demonstrations, the demonstrator will likely never learn how to become a better teacher. Additionally, in human-machine interaction, we aim for the human and machine to have a shared understanding of how best to accomplish the task. And if we're correcting for suboptimality under the hood, this will likely never happen. And so therefore, we posit that in some circumstances, robots should work with their human demonstrators to help them become a better teacher. And so to do this, we revisit our previous example from our MyMeld work, in which we learn this personalized embedding describing the suboptimality of the demonstrator. However, in this work, instead of using this personalized embedding to map suboptimal demonstrations to better demonstrations, our goal is to take the information that's encapsulated in this personalized embedding about the suboptimality of the demonstrator to provide informative and actionable robotic feedback to the demonstrator about how they can improve upon their demonstrations. We call this approach reciprocal MyMeld, and it's based upon the idea of reciprocal teaching, in which the student takes on the role of a teacher. And so our reciprocal MyMeld architecture is based upon our MyMeld architecture, in which we learn this personalized embedding. However, our goal in this work is to shift the personalized embedding closer to that of a perfect demonstrator. We do this in 3 steps. First, we learn a semantically meaningful embedding space so that we can provide feedback to the demonstrator. Based upon where a demonstrator falls within this embedding space, we then provide informative robotic feedback to improve upon their demonstrations. And then lastly, our goal is to update our estimate of where their embedding has moved to after receiving robotic feedback to determine if we should continue to provide feedback or if their demonstrations are acceptably high quality. And so we again demonstrate our reciprocal MyMeld approach in our driving simulator domain. And before we can provide robotic feedback to a demonstrator, we first need to determine what are the ways in which a demonstrator can be suboptimal. And so we found in our MyMeld work that in this driving simulator domain, some demonstrators tend to undercorrect, meaning they don't turn the wheel enough. Others tend to overcorrect, meaning they turn it too much. Others tend to be delayed, meaning they don't turn it soon enough. And then others tend to be anticipatory. So now that we have this understanding of the ways in which a demonstrator can be suboptimal, we can use this information to communicate to a demonstrator how to improve upon their suboptimality. And so one of the assumptions in this work is that the dimensions of suboptimality can be determined by a domain expert. And so given this information, we next conduct a series of 3 human subject studies to determine if robotic feedback can improve upon the suboptimality of a demonstrator, and if this actually results in better learning outcomes for the agent. So in our first study, we investigate if we can improve upon demonstrator suboptimal tendencies just in one dimension of suboptimality. So specifically in the over-under correcting dimension of suboptimality. To do this, we have participants first complete the calibration tasks that were developed in our MindMeld work. From these tasks, we then learn their personalized embedding, describing the way in which they're suboptimal. And then we provide robotic feedback based upon where their embedding falls. And then we have the participants redo the calibration task to gain a ground truth understanding of where their embedding has moved to. And then they do this for 4 rounds, with the end goal being to determine if a participant's embedding moves closer to that of a perfect demonstrator. And so here we see our embedding space that's trained on real human data. And so each point in this embedding space represents a demonstrator and the way in which that demonstrator is suboptimal. We train a support vector machine to separate undercorrectors from overcorrectors and those who are anticipatory from those who are delayed, with the additional constraint that this solution must pass through the point representing the perfect demonstrator, shown here with a black diamond. Our goal then is to provide this robotic feedback to shift the embedding of a demonstrator closer to the perfect embedding. We do this by taking the distance between a demonstrator's embedding and the decision boundary. And then we break this distance into quartiles. And we provide feedback based upon the quartile that a participant falls within. So for example, if they fall in the 4th quartile, meaning that they're a pretty bad demonstrator, we tell them to turn the wheel a lot more or a lot less, depending on if they're an under or an overcorrector. If they fall in the 1st quartile, meaning that they're in the top 25% of demonstrators, we tell them that their feedback is good. And so in our first study, we investigate 3 conditions. We first have a cooperative agent condition in which the agent provides feedback intended to improve upon the demonstrations of the participant. We additionally have an adversarial agent condition, which provides feedback intended to make the demonstrator a worse teacher. And then lastly, we have a none condition in which no feedback is provided. And so here we see the results from this first study. And we show in blue that our cooperative agent results in the personalized embedding moving significantly closer to the perfect embedding. Interestingly, we found that participants did in fact listen to the adversarial agents and that their demonstrations became worse and that their embedding moved significantly farther from the perfect demonstrator. And so our takeaway from this study is that personalized robotic feedback can shift a demonstrator's embedding in this over-under correcting dimension of suboptimality. And so now that we've determined this, we next want to investigate what is the best method for providing robotic feedback in multiple dimensions of suboptimality. And so we conduct another study that has the same procedure as our first one, in which we investigate this question. And so in this second study, we again have 3 conditions. The first is a simultaneous agent condition. And in this condition, the agent provides feedback in both the over-under correcting dimension and the anticipatory delay dimensions at the same time. Our concern, though, is that this may be too much information to provide to a participant all at once and may result in cognitive overload. So we additionally include a condition that we call a greedy agent condition that provides feedback only related to the dimension that the demonstrator is worse in. And then lastly, we have a none condition again. And so here we see the results, and we find that our simultaneous agent results in participants' embedding moving significantly closer to the perfect embedding, suggesting that the additional information that's provided to the participant outweighs the cost of the additional mental load. And so our takeaway from this study is that simultaneous results in the embedding moving closer to that of the perfect demonstrator. And so now that we've determined this, our final objective is to see if providing this robotic feedback actually results in better learning outcomes for the agent, as this is our end goal of doing all of this. And so additionally, in this study, we don't want to have participants continuously have to redo the calibration tasks to gain an understanding of where their embedding has moved to. So in this study, we train what we call an embedding predictor network that learns to predict where a participant's embedding has moved to after they've received robotic feedback and when they're teaching the agent on some novel task. Here we see the results of this third study, and we show that a robotic agent that is trained by a demonstrator who has received robotic feedback results in the agent achieving a significantly lower average distance from the goal compared to an agent that is trained by a demonstrator who's never received feedback. And so our takeaway from this third study is that robotic feedback is able to produce better learning outcomes for a robotic agent. And so thus far in my talk, I've discussed how we can account for heterogeneous abilities of end users. And I've introduced approaches that enable a machine to gain a personalized understanding of their end user, utilize population context, and then optimize the interaction. And so next, I extend these approaches to account for heterogeneous preferences amongst end users. Prior work has shown that end users' preferences tend to be very heterogeneous with regards to the driving style of autonomous vehicles. And prior work has shown that personalizing driving style can increase trust and acceptance of autonomous vehicles and can even decrease motion sickness. However, it's been shown that simply mimicking an end user's own driving style may not be the optimal choice, and that the level of aggression of the driving style can impact preference. And so in my work, I aim to take this information that's been found in prior work and improve upon the personalization of autonomous vehicle driving styles, and thereby increase end user acceptance. We call our approach to this problem Maverick, or manipulating autonomous vehicle embedding region for individuals' comfort. In our Maverick work, we asked two research questions. First, can we observe a participant's driving behavior and use this data to learn to mimic their driving style, as well as be able to adjust the level of aggression? And then, because we know that not all end users will necessarily want the AV to mimic their driving style, we also investigate what factors modulate homophily. And so here we define homophily as a tendency to be attracted to a style similar to one's own. So for example, if someone really doesn't trust their autonomous vehicle, they may not want it to drive as aggressive as they would drive. If they really trust it, they may be fine with it driving as aggressive. And so we're interested in investigating these potential factors. And so we investigate these questions in the domain of light traffic, in which an ego vehicle encounters various leading vehicles and must make decisions about when to change lanes, following distance, and other factors. I did this work in collaboration with Toyota Research Institute, and we use their driving simulator that's a 6 degree of freedom platform and is capable of accurately simulating the physics of a real vehicle. And it also has all the bells and whistles of a standard vehicle. The way our approach works is we have a demonstrator come in and drive in the simulator, and then we collect data related to their driving style. We then use this data to train a personalized neural network that learns to output the high-level control parameters to have the AV be able to mimic the end user's own driving style. So for example, we would learn to output the desired velocity and when lane changes should occur. And then these high-level parameters are fed into low-level controllers to actually execute the lane change and determine the throttle and steering. And so the reason we separate this into a high-level controller and low-level controller is so that we can, if desired, impose safety constraints on the outputs of our high-level controller. So for example, we could cap the maximum velocity. And so here we show our Maverick framework, which learns this personalized embedding W. That describes the driving style of an end user. And so this personalized embedding, along with the candidate or the relevant state information, is then fed into the subnetworks to predict the following distance of the end user, predict when a lane change should occur, and the velocity. And so we train this network to predict the high-level control parameters to mimic an end user's own driving style. But as I said, mimicry may not always be the best option. So we additionally include this subnetwork that we call the style predictor subnetwork. And this subnetwork takes as input the personalized embedding and learns to predict the subjective aggressive style of the driver. And we determine this via a self-reported questionnaire at the beginning of the study. And I'll talk in a minute about why this is important for our framework. And so we next conduct a human subject study in which we investigate the abilities of Maverick to effectively mimic the driving style of an end user, as well as produce more aggressive and less aggressive driving. Here we see the embedding space that's trained on a set of training participants, and each point in this embedding space represents an individual driver and their driving style. And so the way this works is we have an end user come in and drive in our simulator, and we learn their personalized embedding based upon this data that we collect. We then have each end user experience 4 autonomous vehicle conditions. And so this first autonomous vehicle condition is what we call the mimic condition. And in this condition, we use the personalized embedding that we've learned from the end user's driving data to then have the autonomous vehicle mimic their driving style. However, we want to also investigate if some end users prefer a more aggressive or less aggressive driving style relative to their own driving style. And the way we can do this is we can use this subnetwork that I mentioned earlier that learns to predict the subjective aggressive style from the personalized embedding. Because we do this, we can take the gradient with respect to the personalized embedding, and we can determine the gradient of aggression within embedding space. And so then this allows us to move the learned personalized embedding along the gradient of aggression to produce more aggressive driving style. And so this is our second condition, the aggressive condition. We can also move this embedding in the negative gradient of aggression to produce more cautious driving style. And then our fourth condition is more of an exploratory condition, and we call this condition perpendicular. And in this condition, we shift the personalized embedding within the plane perpendicular to the gradient of aggression. And so we're essentially holding aggression constant while changing other latent factors related to driving style. And so here I show some examples of the different driving styles produced by the conditions compared to the participant's own driving style. And so we see that the aggressive condition results in vehicle, whereas the mimic condition chooses a similar velocity as a participant, similar time headway, and more similar driving style. The perpendicular condition in this example exhibits fairly different behavior, and in this case doesn't even choose to pass the leading vehicle, but it selects a similar velocity as the participant. And then we see in the cautious behavior, much more cautious style, more careful lane change, and slower velocity. I also evaluate our Maverick framework with regards to objective and subjective metrics. And so we investigate mean velocity for each of the conditions, mean headway time, distance headway merge back, mean number of lane changes, and time headway merge back. And so each of these objective metrics have been used in prior work to evaluate driving style. And we show that our mimic and perpendicular conditions result in more similar driving style compared to the participant's own driving style relative to the aggressive and cautious conditions. And we show that we show that aggressive produces more aggressive driving style, and that cautious produces more cautious driving style. Additionally, we ask participants to rate their subjective perception of the driving style for each of the conditions. And we find that participants rate mimic and perpendicular as more similar in terms of aggression to their own driving style. And so, as predicted by prior work, we found that even though mimic objectively is able to produce a similar driving style to the participant's own driving, we found that over 20% of participants preferred a more aggressive driving style relative to their own, and over 25% preferred a more cautious driving style relative to their own driving style. And so next we wanted to investigate why some participants preferred a driving style that differed from their own. To do this, we conducted a correlation analysis to investigate which latent factors may impact preference. Interestingly, we found that personality had a large impact on the effect of homophily, and that participants who self-reported being higher in conscientiousness rated the more cautious driving style as being more competent. Additionally, we found that participants who self-reported having a higher velocity driving style rated the more aggressive condition as being more competent. And then in keeping with prior work, we found that participants who reported a driving style to be more similar to their own rated it as more competent. And we found similar results for trust and perceived intelligence. And then interestingly, for discomfort, we found that participants who self-reported being more open to new experiences rated the more aggressive driving style as causing less discomfort. And so to summarize in this work, I introduced our Maverick framework, which can effectively mimic the driving style of an end user, as well as produce more aggressive and less aggressive driving styles. I also showed that personality, high velocity driving style, and perceived similarity impact the effect of homophily. And so thus far in this thesis, I've introduced approaches for accounting for heterogeneous abilities and preferences of end users. However, as I've mentioned, there's many domains in which the safety of the end user must be considered, and the machine's understanding of the safety has to be adapted for every end user. Healthcare is a domain in which safety and the biology of end users must be taken into consideration. And so in my next work, I investigate how we can account for heterogeneous biology as well as safety of a patient in a deep brain stimulation domain. And so in this domain, an electrode is implanted in a patient's brain, which emits an electrical signal. And this electrical signal can be used to reduce symptoms in patients that have diseases such as epilepsy and Parkinson's. The downside, though, is that this electrode is implanted in a different location in every patient's brain. Every patient has different anatomy, and the disease is different for every patient. And so it can be difficult for surgeons to determine the optimal parameter settings for a specific patient. Additionally, surgeons must also avoid dangerous configurations that could induce a seizure or unwanted side effects in patients. And so in this domain, both the biology and the safety of the patient must be considered when determining the optimal parameter settings. And so our solution to this problem is what we call safe meta-active learning, or safe METAL. In safe METAL, we meta-learn an acquisition function that describes the information gained for the brain model of the patient when applying a specific parameter to the patient's brain. This acquisition function is conditioned on the previously experienced brain states and parameters of the patient. And additionally, we include safety constraints to make sure that parameters are not selected that could cause unwanted side effects. And so our objective is to both maximize information gain and safety. And so here we see our safe METAL architecture, and I'll break this architecture into each of its components. Our safe METAL policy selects a parameter setting UT that is applied to the patient's brain, resulting in brain state XT. This parameter setting, along with the resultant state, are added to our history of previously experienced parameters and states. At each time step, we retrain our brain model on this new history. And then our safe METAL policy selects the next parameter setting that should be applied to the patient's brain based upon this new history. So here's a more in-depth look at our safe METAL policy. We feed in the history of previously experienced brain states and parameters into a long short-term memory network that produces encoding Z. This encoding Z, along with candidate parameter UT, are fed into our acquisition function, which outputs a Q value. This Q network is then trained based upon the reward derived from our brain model. And the reward here is defined as the % decrease in the error of the brain model. And so intuitively, parameter settings that are selected that result in a greater decrease in the error of the brain model results in higher Q values. We then embed this acquisition function into a mixed integer linear program. And this allows us to impose safety constraints to ensure that a parameter is not selected that results in an unsafe brain state for the patient. Our goal, therefore, is to select a parameter setting that both maximizes information gain for the patient's brain model, as well as maximize safety of the patient. And so here are the results from our safe METAL approach. And we show in blue that our safe METAL policy is able to more efficiently select the optimal parameter settings for a patient compared to baseline approaches in active learning, meta learning, and Bayesian optimization. We also show that our safe metal approach is able to achieve a higher level of safety for the patient. And so to summarize, in my talk, I've introduced our mind-melded framework, which is a personalized approach for learning from suboptimal and heterogeneous demonstrators. I then discussed our method for providing personalized instruction to suboptimal end users, which we call reciprocal mind meld. I then extended this approach with Maverick to account for differing end user preferences in an AV domain. And then lastly, I introduced safe metal, which allows us to impose safety constraints in safety critical domains such as healthcare. And so to conclude, in my thesis, I've introduced and I've shown that personalized models can improve upon human-machine interaction. And I've introduced approaches to enable machines to reason about heterogeneous abilities, preferences, and biology of end users. In future work, I'm interested in some of the ethical questions surrounding personalized AI. As I've shown in all of this work, we require the machines to gather large amounts of information and data about their end user. However, not all end users may be comfortable with machines having access to all this information. So I'm interested in how we can use explainability techniques to increase transparency of these systems, as well as active learning to decrease the amount of data that we actually need to collect. And then in this work, I've touched on how we can increase safety of these systems, but I think that there's still a lot of interesting work to improve safety and robustness of these systems so that they can be deployed in the real world and work with real human end users. And so to conclude, I'd like again to thank my committee members and thank my advisor, as well as thank all my collaborators and my sponsors. I'd like to thank my parents for convincing me to do a PhD in the first place. And I'd like to thank all of my friends and lab mates, a lot of whom are here in the audience today, for their support over these last 5 years and for making a PhD a lot more fun than I thought it was going to be. So yeah, and I guess I'll take questions.
Why don't we start with any questions from the audience here?
I have a question about the reciprocal mind-meld algorithm. So it seems like the assumption that this is making is that there's some offset in the person's mean response in comparison to your outcome. So I would imagine that robots are also harmed from learning from a very heterogeneous user with like big standard deviations in the way that they react. So how, I guess, could you tailor that algorithm to not just shift their overall mean, like being, not overreact quite as much to actually maybe narrow the amount of heterogeneity of the user's demonstration?
Yeah, I think that's a really interesting question, and that's something that, so in human-centered LFD, we definitely see that that's a problem where humans tend to provide pretty heterogeneous demonstrations and they're not consistent, and so this can make it difficult for robots to learn, especially in human-centered LFD, but also in robot-centered LFD. Humans may differ in the way that they're suboptimal. So I think, in human-centered LFD, if humans are being very consistent with their demonstrations, we could use a similar approach in which we learn personalized embedding that describes the specific end user and how they're suboptimal in a human-centric approach, and then use this to map their demonstrations to more consistent ones. So I think we could use a similar approach, but we would just have to adjust, what our inputs and outputs are to account for consistency rather than just looking at like suboptimality in regards to like magnitude and amplitude. Yeah. Yep.
Hey, great talk. It was really interesting to hear from a robotics field that isn't even close to my own. Actually, still, well, they kind of understand it. So thank you for that. In terms of the human-centric versus robot-centric, for anyone or any people trying to look to combine those so that you have like an expert demonstration as your goal, and then as it tries to meet that goal, kind of correctly along the way?
Yeah. So there have been approaches. There's an approach called human-gated dagger basically, where it starts out more as human-centric, and then once the robot gets off track, then the human can intervene and show the robot how to get back to the optimal path. The problem with some of this work is that we still don't have necessarily the guarantees that we have with Dagger, which is why we chose to improve specifically on the robot-centric LFD approach. But yeah, there are other approaches that try to combine those.
Just a follow-up question. So we work with human loop optimization to optimize our torque controllers for massive skeletons, for example. And what we find is that when working with people, time is a factor. The number of iterations of measurements are a factor. And so we try to limit our parameter space in order to deal with that. Did you have a similar issue, or did you have to contract your parameter space to deal with time limits or things like that?
What do you mean by parameter space?
So when we're talking about, say, for like aggressive driving, right? So you had your kind of, well, actually, I'll go back to the feedback, right? So you had overestimation, underestimation, and delays, right? And so you kind of have two
dimensions.
Yeah, so two parameters,
Yeah. So for that domain, because the human is just inputting corrective feedback with a wheel, so they are providing some signal to the robot. The signal can either be shifted in terms of amplitude or position and time. So those really end up being the two dimensions of suboptimality that arise in that domain. But in other domains, there will definitely be more different dimensions of suboptimality. So that's in future work, we're looking at how we can use our mind meld approach in a robotic arm domain. And so in that domain, the input is with a joystick in X, Y, and also velocity. And so we're going to have additional dimensions of suboptimality in that domain. Yeah.
And you think that your method will be able to scale?
We're hoping, yeah. That's what we're looking at right now. But that's our hypothesis. Yeah.
All right, we will switch to getting the community members an opportunity. The desktop.
We're in Zoom here, though. So, we tested it before. He's just not unmuted. I don't know if he can hear me. Yeah, but I don't know if he can hear me. Are you in Zoom right now? Can you see if you can hear me?
Yeah, unmute my.
We can only hear Mariah. Okay. Right. You asked the committee for questions.
Okay. Yeah, okay, so we're asking the committee now for questions from furthest to nearest. So Dr. Smart, if you have any questions that you would like to ask now, feel free to ask.
Sure. Let me start with one and then I'll pass it on after one and maybe circle back later. So the driving example is great, but it's an instance of sort of one-dimensional feedback. And so it's easy. Not easy. You can take an embedding space, you can figure out where they should be in the embedding space, and then you can translate that back to them saying drive, turn more or turn less. How does this scale to tasks where it's not a one-dimensional correction that they're trying to do? So maybe it's a steering wheel and a gear shift and 3 pedals or something. Like how do you do the credit assignment problem of that and then produce feedback that's actionable for them? Or can you? Does it extend in that direction?
Yeah, so I think
that's.
Yeah, I think that's a really interesting question. And it's something that we're looking at in future work. Like I said, we're looking at if we can do this in a robotic arm domain, which, that probably has a couple more dimensions of suboptimality. It may still not be that complex. And so I think, in this domain, we found that providing feedback simultaneously about both dimensions of suboptimality was effective. But I think as you increase the dimensions of suboptimality, it may be more and more difficult for an end user to receive that feedback and adjust their demonstrations. And so I think, you know, having, like, we had the gritty agent in that study. I think when we have more dimensions of suboptimality, it may be better to communicate to the demonstrator just the dimensions that they're worst in and try and improve upon those dimensions. I think also in some domains in which the dimensions are just too complex, like if you're teaching someone how to play ping pong or something like that, I think simple verbal communication may not even be the best method for improving upon suboptimality. I think potentially having the robot demonstrate and teach by examples may be a better strategy, because then we wouldn't have to actually determine what are all these dimensions. Instead, the robot could just show examples of what better looks like to the demonstrator, and then hope that they can adjust their policy to match what better would look like.
Yeah, that makes sense. Do you ever feel, I realize you haven't done the work yet, but do you ever feel where that break-even point would be? Like, you can tell me the stick shift and the steering wheel, like where does it change from one mode to the other, do you think?
Yeah, I don't. There may be, you know, literature on like cognitive overload that talks about at what point is it too much information, and I think we could go to that literature to try and, you know, get some intuition about at what point it may be too much for a demonstrator to be able to correct. But I think, you know, as we're investigating these questions in higher dimensional domains, we may also be able to gain a better understanding, like with the robotic arm domain that we're looking at.
All right, cool. I'll pass it on to someone else, and then I'll circle back later.
All right, Dr. Howard, do you have any questions for me at the moment?
Yeah, no, I have some for our closed session, but not any for general understanding.
All right, no, Dr. Fye?
I could piggyback on Bill's comments a little bit. That was probably one of my questions. So whether or not I'll answer the question. You can decide whether you want to go deep now with everybody waiting, or if you want to put it off till later. And it was just kind of these extension questions. Like, I think this was a beautiful presentation. I just want to say that right up front I think this was the most seamless presentation I have ever seen in a thesis defense. Like, just beautiful, very well done. Very nicely done. So most of my questions are just kind of about like, how do you extend it? What are the limitations of what you've done and things like that? So again, going back to Bill's when he was talking, my question was just, how do you extend it beyond systems that are inherently designed for human control, right? So we've designed boats and planes and cars, all specifically designed for humans to control them. And historically, that's how we've done it. And so you can get good feedback from humans theoretically, maybe not optimal feedback, for people that do this every day. They do it semi-successfully, right? But when you go to this arm thing, when you go to something else that was never necessarily inherently designed for the human to control it, or specifically designed for that, or maybe we don't have a lot of good people, like, how robust is it, right? How bad can people be? Can you take somebody with a learner's permit and make them better? Do they have to at least have had some experience? Then there's always the questions about, like, I love the question of the clutch, right? Like, can you teach them how to do a clutch? Questions about, right, and you've mentioned this, you've touched on this, like, maybe a verbal explanation is not the best thing. Maybe you should give them some sort of visual feedback. So like they turn it enough, they get into some sort of green zone or something. These are the types of questions and discussions I'd love to hear you pontificate on, but we can do that in closed session, or we can do it now. It's really up to you.
Yeah, I can, give some of my thoughts now, and then we can continue in the closed session. So I think for our MyMeld approach, in which we're, just correcting for suboptimality under the hood, I think if we're able to learn this embedding space that describes suboptimality, and as long as the person that we're trying to improve upon, as long as they fall within this distribution of our training participants, I would hypothesize that we would be able to correct for suboptimality, even in more complex domains or domains that aren't designed for human control. I think with reciprocal MyMeld, in which we're trying to provide feedback and improve upon the end user, a lot of this just depends on the end user's ability to understand the way in which they're suboptimal based upon the feedback that we're providing. So I think a lot of this would just be like design decisions for how we can better teach an end user. And so, like I said, I think in some domains, providing examples may just be more effective than trying to verbally communicate. Or maybe there's been some prior work, at least in learning from demonstration, that has shown like video tutorials can be better than providing feedback, or even better than providing examples. So I think, there's a lot of areas we could explore, and it just depends. It's probably pretty domain dependent, and depends on how well the end user is able to interpret the feedback that's being provided to them. All right, and then I'll move on, Sonia. Yeah. Mhm. Yeah, so going in at the very beginning, we didn't really know what to, but yes, sorry. Yeah, so Sonia's question was, were the different dimensions of suboptimality something that we hypothesized? Was it something that we expected, or were they something that emerged and that we figured out later on? And so going in, we figured, because the input is a signal from the end user, that their signal, it could be shifted in time or shifted in amplitude. So if we're looking at just one demonstration from an end user, we did hypothesize that these were likely the dimensions of suboptimality. And when we did our mind meld work, we investigated if the location of the learn personalized embedding correlated with under or overcorrecting and anticipatory delays. We wanted to figure out, what our algorithm is learning, does this relate to these dimensions of suboptimality? And we found that it does, that the location of the embedding correlates with tendencies to over or undercorrect or be anticipatory or delayed. And so that's how we arrived at these dimensions of suboptimality. And I think there probably are other latent dimensions that I think are probably more difficult for humans to understand anyways. And so we didn't try and communicate or improve upon those dimensions. So for example, maybe someone's turning the wheel too fast or something like that, or across different demonstrations that they're providing, maybe they're not being consistent. So I think there are potentially other dimensions, but these were the ones that were correlated the most with our embedding space. And so we thought that they were contributing the most to suboptimality, and we could also communicate to end users to improve upon.
Right, so one follow-up question. So a long time ago, when Andrew Moss was a PhD student, she had a paper that showed that when teaching demonstration, if users didn't see progress fast enough, they started to change the way they gave feedback in an effort to figure out what the hell would work to make this thing learn faster. Now, I love you methods have improved, and we do learn faster than we did 15 years ago. But I'm wondering, do people, in your experience, this is purely curiosity, do they stay consistent, or do you also see this effect? Because if they change my understanding is if they change their strategy, might not.
Yeah, that's a really good question. Okay, so Sonia's question was, do people change their strategies? And have we observed that they may change their strategies? And if so, mind meld falls apart. And so I want to just jump to one slide that shows, so here okay, all right, you can see that now. So in our reciprocal mind meld work, we had participants repeatedly do the calibration tasks. And so they're providing feedback over and over again. And we found, interestingly, that when we don't try and improve upon their demonstrations, their embedding doesn't move. So that indicates to us that they weren't changing a whole lot. But one assumption of our mind meld work is that participants don't change. I do think, like, if someone was teaching a robot long enough and it really wasn't learning well, that they would change over time. And so one of the innovations in our reciprocal mind-melt work is we have this embedding predictor network that learns to update our estimate of a participant's embedding. So if they were to change over time, for example, after we provided robotic feedback, or maybe just because of some other reason, we could then predict where their embedding has moved to.
That's for the closed session. So that's it. All right. Everyone should please.
Yeah, so everyone on Zoom who's not part of the committee now needs to leave the meeting.